Okay, I guess we can start. Welcome back, everyone. So this is a pretty big weekend we're going to go over from week 3 into week 4. There's a lot to talk about. If you're in the in-person section, I pretty believe I sent everyone a message that the exam's going to be in this classroom. So also, if you're in the online section, that means there is no class. That's sometimes confusing. Sometimes people log in for a class when you're in the online section. If you're in the online section, I sent you some instructions to either register for taking the exam in the Pocatello Testing Center or the Idaho Falls Testing Center or otherwise. And also, there's a lot we talked about last time. When you're studying for the exam, best thing you can do is get caught up on these homework problems here. My goal is to give you your feedback returned before the actual day of the exam. So even if you're in an in-person section, you sent in hard copies of your homework, I'm going to be grading these over the weekend, and I'll scan your graded homework. So watch your ISU email address. I'll send the feedback directly to that email address. That way, everyone, whether you're in the online section or an in-person section, you'll get your feedback on your homework set from all these sections one way or another. Probably Sunday at the very latest if I'm falling a little bit behind, but if Sunday has to be an all-day thing, then that's how it has to happen sometimes. Sometimes we get really, really busy weeks in this kind of school semester setup that we're in. Another thing that's kind of unfortunate is the math department does have us on a pretty busy schedule, so we don't have review days. But I'm very happy to help out with any exam questions you might have over office hours. Send me direct email questions as you're studying. I'm very happy to help out with that. That's also the reason why we're not trying to rush through these sections. And I'm pretty straightforward with what's going to be on the real exam. If you can solve these problems with confidence, if you miss problems, you know why you missed it, and you can rewrite the solutions with it corrected in it, you're in pretty great shape. If you can run through these sample problems here, maybe targeting sections that seemed a little bit harder, and get through those kind of problems as well, you'll be in great shape for these exams. But any questions at all, folks, about the upcoming exam or otherwise? Okay, well, section 1.3 is due today. I'll begin grading homework sets on Friday. 1.4 is due the day of the exam, which is, again, kind of unfortunate in a certain sense. I encourage you to do that one as soon as possible. And if you do send this in to me early, assignment 1.4, I'll make every effort to get it graded and sent back to you. So if you're in the in-person section, that's kind of tough, but you can also be welcome to scan your work, send it in to my email, and I can grade it that way and send you the feedback back. So that way you don't have to feel like you're waiting till Tuesday. Even if you send me section 1.4 on Monday, I'll make every effort to get that graded and sent back to you. Well, I think that's my full spiel of announcements for today. Any questions whatsoever about the exam or otherwise? Okay, well, let's start where we left off. We opened section 1.5, but I don't believe we did any examples in there. We just looked at how things are connecting so far. So here's where we left off. I guess we did do an example, but example one was more just getting started. We're going to start dealing with the so-called homogeneous systems. A homogeneous system of linear equations just has this feature, whether it's a matrix equation written out as a vector equation or the line-by-line system of equations, the right-hand side is zero. Zero is a vector, or zero is individual scalars in the line-by-line equations. And because of that zero, thinking in algebra as an analogy, we already have a ready-to-go solution. X equals 0 as a vector here would be an automatic solution to a homogeneous system. And because it's an automatic solution, like this one in R3, we call it the trivial solution. It's there canonically, you didn't have to do any work, so we say it's trivial to find it. You just had to know the right-hand side was 0 to get it. So that was our core definition about the trivial solution. The thing that we're really interested in is when non-trivial solutions exist. But we also had a trichotomy, a system of equations, whether it's a matrix equation formatted or otherwise. Either there's zero solutions, none whatsoever, an inconsistent system, or it's consistent and it has a unique solution. Well, a homogeneous system with a unique solution would have exactly one solution, the trivial one. So in our theorem section from section 1.2, when this happens, when there's a unique solution, AX equals 0. Now it's homogeneous, has only the trivial solution. So this is when there's no free variable whatsoever. If the matrix equation X equals 0 does have a free variable, that means there are infinitely many solutions, and all the solutions aside from the zero vector are the so-called non-trivial ones. So all it takes is one free variable, and you have non-trivial solutions. And that's the whole idea with this theorem down below. Our author didn't call it a theorem 3 or theorem 4 because it's just an immediate consequence. It might have been called a corollary. We'll call it a theorem here on the notes. It says the homogeneous equation AX equals 0 will have non-trivial solutions if and only if it has at least one free variable. If and only if in yellow is telling us this is a powerful theorem, the logic goes both ways. If you have at least one free variable, there is a non-trivial solution, and vice versa. If you know there's a non-trivial solution, then there had to have been a free variable. And we've mentioned this before. Sometimes we use the biconditional double-directed arrow just to say if and only if a little bit more faster, just as a shorthand. So really, this theorem is just a rehash of this section 1.2 theorem 2. And to start off the day, we'll determine if this system with augmented matrix has a non-trivial solution. First, any questions, folks, with the definitions or this new theorem down below? Okay, so the question of non-trivial solution is just simply a question of, does it have a free variable? And to determine if it has a free variable, all we need is an echelon form, nothing else. Let me fix this formatting. It's doing something weird here on Microsoft Word. Well, we're told that this has been augmented, so it doesn't hurt to go like that. I'm not too sure what's upsetting Microsoft Word there. Maybe if we just scroll like that, it'll help. Who knows? But because the right-hand side is 0, we can say the matrix equation for this would have been AX equals a 0 vector. Thought that was a highlighter. So starting this off, here is A augmented with that 0 vector again. Sometimes we use this shorthand right here just to connect the dots. That we're taking this entire system, these are the coefficients of the equations, and the part that's been augmented here. I'll begin the row reduction down below. And because we need echelon form, we don't have to do anything with that 2. We can leave it as a 2. Let's keep that 2, negative 5, 8, 0. Now take row 1, directly add it down into row 2 to get 0, negative 12, 9, and 0. Next, we're eliminating the 4 down below. So multiply row 1 by negative 2, add 2 below to get negative 4 plus 4 for 0, multiplying by negative 2, so that's 10 plus 2 for 12. This will be negative 16 plus 7 for a negative 9. And notice something curious, no matter what row operation you do, a column of zeros is forever a column of zeros. It really makes you question if you even needed that column of zeros if nothing's going to change. And you really didn't. If you just left this off, that would have been totally fine, really. There's some contexts where it's better to have it in. If we're trying to solve AX equals 0 and get all solutions, it's sometimes a really good idea to leave that in just for notation, formatting, bookkeeping purposes. Still kind of a judgment call, but I'll usually leave it in to avoid any potential confusion. But getting to echelon form is going well. We have a pivot here. We've revealed a second pivot here. And you might notice row 3 is just completely the opposite of row 1. That means row 3 is just vanished at this point. Add row 2 to row 3, and we get a row of zeros. So the reduction, this one ended quick, is 2, negative 5, 8, 0, 0, negative 12, 9, 0. Add these last 2 rows together, and we get 0, 0, 0, and 0. We now have a pivot in column 1, column 2. That means x1, x2 are basic variables in the system. But column 3 relative to x3 has no pivot whatsoever. This tells us x3 is free. We found at least one free variable, in other words. You don't necessarily have to put the if and only if. Our logic just wants to go in one direction to determine if we have a non-trivial solution or not. So I would go like this. X3 is free implies, or we can just literally write implies, there's no harm done, implies there are non-trivial solutions to AX equals 0, that matrix equation. That tells us something really fundamental about the columns out of nowhere that I really wouldn't be able to really see if I squinted hard enough and looked at this. Maybe if I looked at the columns hard enough, you might have noticed that one of the column can be written as a linear combination of the other two. But I think it takes some really fast arithmetic. Some people do have the eyes for this. They're amazing. But I usually have to work out the details to determine that or not personally. We resolved the question, folks. There's a non-trivial solution. So that means, sure, you can put 0 here for x to get that 0 vector on the right-hand side. But there are non-zero vectors you could pick here to also get the solution set equal to 0. Any questions at the moment with what we've done so far? Okay, just an additional comment because it'll become important in already the very next section, 1.7 that we're covering. The fact that there are non-trivial solutions means the columns of A are linearly dependent. We haven't formally defined that yet, but this is actually the definition in the very next section. Probably a good idea to start thinking about this. Non-trivial solution says there is a dependence relation among the columns. One of those three columns, any one of those three, can be written as a combination of the other ones linearly. That's kind of strange in a sense, and that's what the next section is going to be all about. So think of 1.5 as just kind of the bridge to get to those concepts. So that's how an example 2 kind of question will go. Let's try this again for just more variety with this topic. This one's different because they didn't give us an augmenting matrix. We haven't written down a matrix equation either. This is just the ordinary system of equations. This is something we could have looked into in section 1.2, for example, or maybe even 1.1. We're asking, is it possible for the system to be inconsistent? What do you folks think? Is there any way that this is inconsistent? And class folks are saying no. And I totally agree. If you've got zeros here, we could have answered this in section 1.1, right? One solution is just picking x1 is 0, x2 is 0, x3 is 0. That'll balance the first equation, 0 equals 0. Same exact choice balances the second equation and the third equation. So it's a homogeneous system of equations. So we can say, no, it is consistent because that's a fire alarm. Sorry, folks, we have to call class at this point. Kind of weird when this happens, but